Retrieval Augmented Generation, or RAG, is an approach that combines the generative capabilities of large language models with the precision and grounding of information retrieval systems. The motivation behind RAG is clear. Large language models are trained on massive datasets and encode a huge amount of statistical knowledge in their parameters. They can generate fluent, coherent text and answer questions across a wide range of topics. However, they are limited by the data they were trained on. Their knowledge is frozen at the time of training, and they cannot easily access new information. They may also hallucinate, producing outputs that sound plausible but are factually incorrect. RAG addresses these limitations by giving models the ability to consult external sources of information during inference, grounding their outputs in retrieved documents or passages. This makes them more accurate, more current, and more trustworthy. The process begins with a user query or prompt. Instead of relying solely on the model's internal parameters, the system first encodes the query into an embedding vector. This embedding captures the semantic meaning of the query in a high-dimensional space. The embedding is then used to search a database of documents, passages, or knowledge entries. This database has been pre-processed so that each document is also represented as an embedding. Similarity search identifies the documents most relevant to the query, typically using measures like cosine similarity. The top K documents are retrieved and passed along with the original query to the language model. The model then generates a response that integrates both its internal knowledge and the retrieved information. The result is a response that is fluent and contextually grounded in external data. To understand this process more deeply, let us consider the mathematics of embeddings and similarity search. Suppose we have a query represented as a vector Q road, where D is the dimensionality of the embedding space. Each document in the database is represented as a vector D road. The similarity between the query and a document can be measured using cosine similarity, sin Q, D equals QD QD. This measures the angle between the two vectors, capturing semantic similarity regardless of magnitude. The retrieval system selects the top K documents with the highest similarity scores. These documents are then concatenated with the query and fed into the generator. The generator, typically a transformer-based language model, uses attention mechanisms to integrate the retrieved information into its output. This process allows the model to ground its responses in external evidence. Dense retrieval systems rely on embeddings learned by neural networks. These embeddings capture semantic meaning, allowing retrieval to go beyond keyword matching. Sparse retrieval systems, such as BM25, rely on inverted indexes and term frequency measures. They are efficient and interpretable but limited in semantic understanding. Hybrid systems combine both approaches, using sparse retrieval for recall and dense retrieval for precision. For example, a hybrid system might use BM25 to identify a broad set of candidate documents and then use dense embeddings to rank them more precisely. This combination leverages the strengths of both methods. The architecture of RAG involves several components. The retriever is responsible for encoding queries and documents into embeddings and performing similarity search. The generator is the language model that produces the final output. The retriever and generator can be trained separately or jointly. In joint training, the retriever is optimized to provide documents that improve the generator's performance. This creates a feedback loop where retrieval and generation reinforce each other. In separate training, the retriever is trained independently, often using contrastive learning, and then integrated with the generator. Both approaches have advantages, and the choice depends on the application and resources. Training RAG involves teaching the generator to use retrieved documents effectively. During training, the model is given queries along with relevant documents and learns to generate outputs that incorporate the retrieved information. Negative examples, where irrelevant documents are provided, help the model learn to ignore noise. The reward signal can be based on accuracy, relevance, or human feedback. Over time, the model learns not only to generate fluent text but also to ground its responses in retrieved evidence. This reduces hallucination and improves trustworthiness. RAG has important implications for scalability. Instead of encoding all knowledge in the parameters of the model, which requires massive training and storage, knowledge can be stored externally in databases. The model only needs to encode general linguistic competence and reasoning ability. Specific knowledge can be retrieved as needed. This makes models more efficient and adaptable. Updating knowledge becomes easier, since the database can be refreshed without retraining the model. This separation of competence and knowledge is a key advantage of RAG. Consider an example in medicine. A language model trained in 2023 may not know the latest clinical guidelines published in 2025. Without retrieval, it may provide outdated or incorrect advice. With RAG, the model can retrieve the latest guidelines from a medical database and generate responses that are both fluent and current. This makes the system more reliable and useful in practice. Similarly, in law, a model may not know recent court decisions. Retrieval allows it to access legal databases and provide responses grounded in current precedents. In education, retrieval enables models to reference textbooks or lecture notes, providing accurate explanations. In customer support, retrieval allows models to consult product manuals or FAQs, ensuring that responses are consistent with official documentation. The mechanics of retrieval also involve considerations of efficiency. Embedding large document collections requires significant computation and storage. Vector databases, such as FICE or MILVIS, are optimized for high-dimensional data and can handle millions of documents efficiently. They use techniques like approximate nearest neighbor search to balance accuracy and speed. Indexing strategies, such as hierarchical clustering or product quantization, further improve efficiency. Engineers must design retrieval systems that scale to large corpora while maintaining low latency. Integration with generation is another critical aspect. The retrieved documents must be presented to the language model in a way that it can use effectively. This often involves concatenating the documents with a query and feeding them into the transformer. Attention mechanisms allow the model to focus on relevant parts of the retrieved text. However, simply concatenating documents can be inefficient, especially if they are long. Techniques such as passage ranking, chunking, and selective attention are used to ensure that only the most relevant information is included. Some systems use retrieval condition generation, where the model explicitly attends to retrieved passages during decoding. This makes the integration more structured and reliable. Let us now look more deeply into evaluation, applications, ethical considerations, and future directions of retrieval augmented generation. One of the most important aspects of RAG is evaluation. Traditional metrics like BLEU or Rouge measure similarity to reference texts, but they do not capture factual accuracy or grounding. Evaluating RAG requires metrics that assess whether the generated output is supported by retrieved evidence. This involves checking consistency between the output and the documents, measuring factual correctness, and assessing relevance. Human evaluation is often necessary, since grounding is a nuanced property. Researchers are developing automated metrics for grounding, such as fact-checking algorithms that compare outputs to retrieved passages, but this remains an active area of work. Applications of RAG are diverse and impactful. In question answering, RAG allows models to provide answers that are not only fluent but also supported by evidence. For example, a user might ask about the latest scientific discovery. A pre-trained language model without retrieval might hallucinate or provide outdated information. A RAG system can retrieve recent articles from scientific databases and generate an answer grounded in those sources. In summarization, RAG can ensure that summaries are based on actual documents rather than hallucinated content. This is particularly important in journalism, where accuracy is critical. In dialogue systems, RAG enables chatbots to consult knowledge bases, providing accurate and up-to-date responses. In code generation, RAG can retrieve documentation or examples to guide output, making the generated code more reliable. In medicine, RAG can ground responses in clinical guidelines, reducing the risk of unsafe recommendations. In law, it can reference statutes and precedents, ensuring that outputs are consistent with legal frameworks. In education, it can provide explanations supported by textbooks, helping students trust the information they receive. In customer support, RAG can consult product manuals or FAQs, ensuring that responses are consistent with official documentation. Case studies illustrate the power of RAG. Consider a medical assistant designed to help clinicians. Without retrieval, the assistant might rely on outdated knowledge, potentially leading to harmful advice. With RAG, the assistant can retrieve the latest clinical guidelines and research papers, grounding its responses in current evidence. This makes the system safer and more useful. In legal practice, a RAG-based assistant can retrieve relevant statutes and precedents, helping lawyers prepare arguments. This reduces the risk of hallucination and ensures that outputs are legally sound. In education, a RAG-based tutor can retrieve passages from textbooks or lecture notes, providing explanations that are consistent with the curriculum. This builds trust and enhances learning. In customer support, a RAG-based chatbot can retrieve product manuals, ensuring that responses are accurate and consistent with official documentation. These case studies show that RAG is not just a technical innovation but a practical solution to real-world problems. Ethical considerations are central to RAG. Because retrieval involves external sources, the quality and bias of those sources directly affect outputs. If the database contains biased or misleading information, the model may propagate those biases. Addressing this requires careful curation of databases, transparency about sources, and mechanisms for correction. Privacy is another concern. Retrieval may involve sensitive data, such as medical records or personal documents. Systems must ensure that retrieval is secure and that outputs do not expose private information. Governance is also important. Who decides which sources are included in the database? How are updates managed? How is accountability enforced? These questions must be addressed to ensure that RAG systems are trustworthy and fair. RAG also raises questions about interpretability. Users may want to know why a particular output was generated and which documents were used. Providing citations or references helps build trust. Some systems display the retrieved documents alongside the generated output, allowing users to verify the grounding. This transparency is valuable but must be balanced with usability. Too much information can overwhelm users, while too little can reduce trust. Designing effective interfaces for RAG is an important area of research. Looking to the future, RAG will continue to evolve. Advances in retrieval models will improve semantic understanding and efficiency. Integration with multimodal retrieval will allow models to consult not only text but also images, audio, and video. For example, a multimodal RAG system could retrieve both text descriptions and images to answer a question about a medical condition. Real-time retrieval will enable models to access dynamic data, such as live news or sensor streams. This will make systems more responsive and current. Personalization will allow retrieval to be tailored to individual users, though this raises privacy concerns. Hybrid approaches will combine retrieval with symbolic reasoning, grounding outputs not only in documents but also in structured knowledge bases. This could enable models to perform more complex reasoning tasks, such as legal analysis or scientific discovery. Ethical frameworks will shape how retrieval systems are built and used, ensuring fairness, transparency, and accountability. From a technical perspective, RAG continues to push the boundaries of both retrieval and generation. Training large language models with retrieval is challenging because the action space is enormous and the outputs are complex. Traditional retrieval systems were designed for keyword search, not for integration with generative models. Applying retrieval to language requires innovations in embedding models, similarity search algorithms, and integration strategies. RAG has driven progress in these areas, contributing not only to language modeling but to information retrieval research more broadly.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.